Okay, welcome. So what I'm going to try and do today is cover some of the just sort of an outline of the extent to the mathematical skills that we'll be using. So gonna cover a few different things here. Let's see, can I share? There we go. Whoops. And there we go. Okay, I think that's right. All right. So here are the notes. So first thing I want to talk about is significant figures. Now, if you recall from the last lecture, what I was saying about significant figures is basically that the reason it's important to pay attention to significant figures is you want to use a number of significant figures that communicates, how well you know the number that you're reporting. Okay. So I'll eventually give you the rules for significant figures, but here's the main idea. And if you pay attention to this main idea and you kind of use this as your guiding star, I think you'll probably be okay. I'm not going to be super strict about testing the rules to see if they're all right, and we'll talk about why that's the case. But in the short of it is that it's not always clear what the rules are. We can talk about it for some operations, but it's harder to for others. So when it comes to significant figures, the main idea that you want to do is you want to round to a place that indicates, I'll put this in put approximately how well or how certain you are about the result. We'll just say how certain you are about the result. Okay. So the idea is like if you're rounding to a speed and you have, you have 7 decimal points after meters per second, that's going down to saying you were measuring, you are confident enough in your experiment that you were measuring at a level of micrometers per second. And there's no way that that's true. Okay. So the idea is like when you ask about rounding, just keep this in mind. Like how well or how certain are you of the the number that you're rounding to? That's kind of how it works in lab. If it works for problem, if you're trying to decide, in a story problem, what to round to, think about the how well, how specifically they've specified the numbers they've given you. Okay, because if they've only gone to 1 decimal point in the numbers they've given you, you shouldn't go any further than that in the numbers you report, because basically what that 1 decimal point is saying is it's saying that this is basically it rounds to this number. That's what it's saying when the actual value, it rounds to this number. All right, that's kind of what they're getting at there. Okay, so that's the idea for significant figures. Now I will give the significant figure rules as well. So here is rule 1. Any non-zero is significant. Now, when we say it's significant, what we mean by this is it's telling you something about how well you could measure about how well you measured the quantity. Okay. Sometimes digits don't tell you that, they're just placeholders. So if you were measuring, you could measure some number of meters, but you could report it in micrometers. Now, and if you were to do that, then you'd have a lot of extra zeros at the end, but those would not necessarily be significant. All right. Second, any zero between non-zeros. This is also significant. All right. Now, third thing that is significant, any trailing zeros. By trailing zeros, we mean zeros to the right of any significant any digits we know are significant. So basically any to the right of any non-zero number. Any trailing zeros to the right, and I'll capitalize this because not all trailing zeros are significant. A lot of times they're not, but if they are to the right of a decimal point, then they are significant. All right. And then so put a dash there, and we'll say for any trailing zeros to, as I say, any trailing zeros if no decimal point is present. All right. If a decimal point is present, then all the trailing zeros will be significant. Okay. So I'll put that in notes. If decimal point is present, trailing zeros, and this is any trailing zero, is significant. Trailing zeros, I should say are instead of is, are significant. Okay. And then last thing, leading zeros. So basically leading zeros are zeros to the left of any significant figures. Those are all not significant. They would just be placeholders. A lot of times you don't even put them. Leading zeros are not significant. All right. So to give a few examples of this, we had say 1.06. This would have three significant figures. The 3SF. The 1 and the 6 are both significant, and because the 0 is in between the two, it is significant as well. If we had, say, 2,000, this is just one significant figure. Here's what I was talking about if a decimal point is present. If we have 2,000 and then a decimal point, you'll see this written occasionally. And the reason they write that decimal point there is to basically tell you that all those trailing zeros are in fact significant. What this first one is telling you is it's telling you that it's about 2,000, which means, you know, it's greater than or equal to 1,500 and less than or equal to, less than 2,500. But if you have the decimal point, it's saying, okay, we know this thing is exactly 2,000 all the way to the ones place. So basically, this is between 1,999.5 and 2,000.5. Okay. So this one actually has four significant figures. If you were to do, say, 4.600, this also has four significant figures. So if you have those trailing zeros after the decimal point, those are also significant. Okay. Like I said, I'm not going to be super concerned about it. When you get to problems and, you know, specific problems and where significant figures are required, it's good to know about them and why they exist, but I'm not going to be super gung-ho about you knowing all the rules right now. I will give you the calculation rules as well. Calculation rules for sig figs. So the idea here is for sig figs, for significant figures. The idea here is that you when you combine quantities with various mathematical operations, you have to know, you know, sometimes they'll have different numbers of sig figs, and you have to know, you know, okay, what's the rounding? How many sig figs do you keep? Okay, So if you're adding or subtracting, then the rule is you round to the same, or I'm sorry, you round to the the same place as the least significant term. Is the least significant quantity. Okay. So, for example, just to give you a simple one, if we had something like this, 10.01 plus 1.5, basically what we'd say is okay, this one has 4 sig figs. This one has 2 sig figs, which means we're going to round not to 2 sig figs, but to the same place as this least significant number. Okay. So we're going to round to the same place as that one. All right. So we'd go, okay, 10 plus 10.01 plus 5.1. This equals 10.5 or sorry, 11.51. But then we have to round to this place. So we're saying round to 10th place. And so we'd say this is equal to 11.5. Okay. Now I'm probably not going to dock you if you wrote that down as 11.1. That's not so I'm not like I say, I'm not interested in being that much of a stickler, but that's basically how you do it. And then for multiplying and dividing, you basically round to the least number of sig figs in of the constituents. Okay, so let me constituents. All right. So an example of this would be as if we had, say, 3.25 times 5. Okay. So the idea here is we'd have this has 3 significant figures, but this only has 1 significant figure. And what this means is that basically what we need to do is we'd multiply this and we'd get, I believe it's 16.25 when we multiply that out. But we have to round to 1 sig fig. So this is the one where we would say, okay, well, we got to round. So round to 1 sig fig. Well, when we round to 1 sig fig, basically that means we can only keep the tens place because that's our most significant digit, and that's the one we need to keep. So rounding 16.25 to the tens place gives us 20. Now that one's a little odd, and this is why oftentimes you will almost always have more than 1 sig fig. You'll almost always have 2. If you have 2, if say we had, I'll do it in a different color, but say we had, 5.0, now it would be 2 sig figs. And then this thing would round to just 16, which is a little bit more reasonable. One thing to note, if you are dealing with a specific number of quantity or a specific quantity of something, so if say like you're doing a money problem and you're buying, say, 5 objects at a cost of 325 a piece, you don't do the sig fig rule with that. Because if it's a specific quantized thing, like you can't buy, in this case, you couldn't buy like 5.1 objects. So that 5 is actually reporting an infinite number of significance because you bought exactly 5. And that's the idea. So in that case, you would just say, oh, it's 16.25. Okay. So that's the idea behind that. But like I said, I'd really just kind of prefer you use kind of your common sense and just go back, keeping this main idea. How, when you round, think about what you're communicating by the place that you're rounding to. Okay. All right. So let's get into some of the mathematical skills that we're going to need. Mathematical skills. Now, these are things that I hope you know coming in. I'm not going to go over how to do much of these. If you're really unfamiliar with these skills, then we're going to have to set up an office hours and go over these as you need to. But basically they fall into two categories: algebraic manipulation and then 1 and 2 trig and geometry. All right. So when I talk about algebraic manipulation, mostly what we're going to be dealing with is polynomials, and then just and equation solving is the idea. That's mostly what we're going to be looking at. When we're talking about trig and geometry, it'll be triangles, and then sine, cosines, and tangents. Those are the main things to know. So I'll just indicate that as a list. And I think what I want to do is just show you a couple of examples for what I'm talking about when I'm talking about these kinds of things. So for example, I'll use something like this. It would, if we had something like 1/2 a t squared plus v sub 0 v naught t is equal to we'll just say 20. The idea here is that if a equals -10 and t equals 3, find v sub 0. Okay, so that's something you might need to do. That's one aspect of this. So you could do this a number of different ways. Another thing you might be asked to do is you might just be asked to find v sub 0 without anything involved there. So if you can find v sub 0 without having these numbers, finding it with the numbers becomes a lot easier. So the idea here that I want you to be able to demonstrate is, you've got 1/2 a t squared plus v naught t is equal to 20. And I want to solve for v naught. So knowing the steps, you subtract your 1/2 a t squared, and you have v naught t is equal to 20 minus 1/2 a t squared. And then if you wanted to solve for v naught, you'd divide both sides by t, and those would cancel, and you just get your v naught was equal to this. Now you can do a equal -10 and t equal 3 if you're so inclined. So that would be 20 minus 1/2 times -10 times 3 squared all over 3. This is going to be 20 and then plus 5 times 9, which would be 65 over 3. So it would be 65 over 3, and that would be your v naught. So that kind of algebraic manipulation, being able to do that sort of on the fly, would be is going to be kind of what you need. I don't expect the algebra to get really any harder than that, but that's kind of the upshot with that. When it comes to trig and triangles, I'll show you a diagram that comes up a lot, or the type of diagram that comes up a lot in these physics classes. So you have, a lot of times in physics, this ends up being a ramp, and you'll have some angle theta. And then what you have here is you have something that's going to go, do a dotted line. And we'll just call this, call that f sub g right there. Okay. And then, and if you're familiar with this, I'll draw the thing like that. You may, if you've seen these kinds of problems before, you may be familiar with this. If not, that's okay. F sub n. And that is perpendicular to that point right there. And then we would have something like this. F sub, just call that F sub P, I guess. And then one of the things you might see is you might see these two little dash marks on these two lines on the F sub n and then the portion of F sub g. So F sub g would be this one right here. That's F sub g. Not G sub g, but F sub g. And then the idea is that these two things are equivalent. So knowing that notation is that they're both F sub n there. And then the question is, okay, could you find F sub P? All right. Sometimes you'll be given numbers, sometimes not. I'm going to solve for it without numbers. But the idea here is that what you want to be able to do is you want to be able to break this down in terms of right angles and right triangle identities. So here's the thing. Some of what you can see here is will be the following. Now, first of all, when you would analyze this thing, I'll do this in a different color. What we would say is we can call this angle, just call it something else. I'll call that phi. Now, one of the things you would need to know is that phi is going to be 90 minus theta. The reason for that is it has to do with the interior angles of a triangle. But that's the green angle that I've indicated right there. Now, I'll do the red angle, this one right here. Now, the red angle, this one is going to be, we'll just call that red. Well, that's actually going to be 90 minus phi. Okay. And the reason there is that if I combine that green looks like it's doing the whole thing. The green is just that one. Is that if I combine these two angles, that makes another right angle because this line with F sub n, it's making a right angle with that slanted surface. Now, the point there is then you have 90 and then minus 90 minus theta. And so your red angle is also theta. That is something that you just kind of get used to seeing, but knowing why that's the case is kind of important. Okay. And then from there, what you can say is you can say, okay, now what I have here, and I probably should have indicated that that's a right angle there, is I have a triangle where I know one of the angles and one or two of the sides. Okay. So what I could do is I could say, okay, well, F sub P. Actually, I should indicate that you might need to figure out F sub n as well. You might not know F sub n. You probably have to figure that out as well. So the idea there is that F sub n, couple of things. Cosine of theta will be equal, and cosine is equal to adjacent over hypotenuse. So in this triangle down here, the adjacent is F sub n and the hypotenuse is F sub g. So that means F sub n would be equal to F sub g cosine theta. And then sine theta is equal to the opposite over the hypotenuse. So in that same triangle I circled, that would be F sub p over F sub g. And that is going to get you, that means that F sub, well, I need the equal sign, but F sub p would be F sub g sine theta. Okay. So that is going to be a very common analysis, and being able to analyze triangles in this way is going to be important for this class. Comes up a lot when we're discussing vectors, which is the last thing I want to cover today. Now, The reason why triangles come up so often in vectors is because basically what a vector is a measured quantity in which direction is relevant. Okay, so direction is a relevant part of the measurement. So the idea here is that, if we're talking about, say, measuring pushes, you might only care about, how big the push is, but you might also care about whether or not the push is moving you to the left or the right. Okay, so the idea is that in certain quantities, sometimes direction is relevant. Okay, sometimes you don't care about it, but oftentimes direction is a part of the thing. Sometimes it's clear. I'll just define scalar. Scalar is the alternative to vector, is direction is either irrelevant or not present. Okay, so to give a sense of a few scalar quantities versus vector quantities, a real easy one for vector is force. When we're talking about forces are just pushes or pulls. And it's in order to understand the behavior of the object, we almost always need to know which direction the force is acting. Okay, particularly if the object is already in motion, because the direction of the force relative to the motion is going to have very different effects depending on what the direction of the force is. Okay, so specifying direction correctly is going to be really important. One where it's clear where there's no direction is temperature. All right. Temperature does not have a direction. Mass also does not have a direction. Okay. Now, sometimes it's not as clear. So, for instance, where does distance go? Well, you may already know this. Now, it turns out distance is a scalar. And basically, that is when in physics, when we use the term distance, we're just talking about the the sort of the length of a path traveled. That's what we mean by distance. If we care about the direction, we can conceive that we might care about the direction. If we do care about the direction, we call that something different. We call that displacement. Okay, we'll get into this a little bit more when we talk about kinematics, but just to introduce this idea. Displacement is basically distance with direction. Another one is speed. Speed is actually the scalar. This is what we're talking about when we're talking about a rate of motion. That is a scalar. And that when we talk about speed, we don't care about the direction. If we care about the direction in physics, we call it something else. We call it velocity. So velocity is speed with direction. Okay, so a lot of times velocity and speed are used kind of interchangeably. They're not interchangeable in physics. It's important to know, and even sometimes if you use the terms interchangeably, it's important to know if you care about direction or not, because that will depend, or that will affect how the problem goes. Okay, so the idea behind vectors is that they need to be represented in a certain way. So, and there are many different ways you can represent direction and quantity. Well, really just two that I'm going to talk about. But the idea, the whole idea is that you need a way to represent both direction and magnitude. So you need, if you're talking about a speed or a velocity, you need a way that indicates both how fast the thing is going and what direction it's pointing. Okay, and there are basically two ways we can do this. So two ways. What we call a polar form. And in a polar form, what this consists of a magnitude and an angle. And then a rectangular form. And when we're talking about rectangular form, what we're doing there is we're representing X and Y components. Now, in either case, we need a reference point, okay? So when we're specifying direction, it needs to be in reference to some either known point or known direction, one or the other. So for rectangular form, the reference point we use will be some origin in a Cartesian plane. Now, a lot of times where that origin is arbitrary. So if you're talking about distance from, you're talking about, okay, distance from your house or displacement from your house. You could either pick where you started as your origin or where you ended as your origin. But the point is you need to have some origin in order to specify that. So that's the idea. With polar form, your reference point or your reference direction will often be your x-axis, because this is defined as an angle of 0 degrees. So when you're talking about an angle of 0 degrees, that generally means your x-axis, okay? And your x-axis, which direction your x-axis is pointing can be, you can do that however you want, but the idea is that you have the x-axis as your reference point, okay? So I want to go through a couple of examples with this. So the idea here, so a couple examples. So for example, a car is displaced, we'll say 100 meters at 30 degrees from where it started. All right, now the idea here is that if we're going to draw a picture of this, basically what this would mean, and this, by the way, this is a polar form. But what we mean by this is that we had the start, and then, it's not quite 30. The thing got moved at an angle of 30 degrees, and the end point was right there. And then this thing was 100 meters. Okay, that is basically what we're saying if we express this displacement in polar form. Now, the idea here is that you could express in rectangular form. Well, in order to do that, basically what you would do, I'll change this to red for that. What you would do is you'd want to know, okay, what is the delta x? How far did it go in the x direction? And then what is the delta y? How far did it go in the y direction? Now to do this, so you want to know delta x equals what? Delta y equals what? Well, to do this, what you need, that looks like 300, that should be 30 degrees. What you need to do is you need to go back to that trig stuff we were talking about. And the idea here is that sine of 30 is going to be equal to the opposite over the hypotenuse. So that the opposite is y. So the idea is we'd have sine of 30 equals delta y over 100. And then delta y is going to be equal to 100, 1,100 cosine of, or sorry, sine, not cosine, jumping ahead, sine of 30. Now, cosine of 30 is going to be equal to the adjacent over the hypotenuse. That's delta x over 100. So delta x is going to be 100 cosine of 30. Okay, so that is how you convert between polar and rectangular form. All right. So that's kind of what's going on with that. Now, the the it will be important to know how to go back and forth between polar and rectangular. Okay, so I also want to do another quick example. Oops. Good. I also want to do another quick example where we go the other way. So we'll say, okay, so for example, a boat is moving northward at 16 meters per second and eastward at 9 meters per second. So the idea here is that it's moving north and east at the same time. It's moving in some northeast direction. We don't know what direction, but we do know that its northward progression rate is 16 meters per second, and that its eastward progression rate is 9 meters per second. So what we could ask is, what is the speed of the boat? Now, it's not 16 or 9 because it's going both north. It's going both north and east. So what we would need to do is we need to do something like this. Is we need to say, okay, this boat, basically what it's doing, it's going, we do know it's going 16 north, but also 9 east. And it's kind of looking like this. Now, hopefully what you realize is that you have another triangle here. And the speed, interestingly enough, a lot of times we use V as a symbol for speed. I'll show you the difference, but we'll talk about the difference between speed and the symbols between speed and velocity in a bit. But hopefully you realize that this is a bit more triangle geometry here, and that what you can do is this should be that 16 squared plus 9 squared should be equal to V squared. So that's a squared plus b squared equals c squared. Now you can go ahead and do that. This ends up being, what is this? This is 256. I think that's right. Plus 81. Is that correct? I don't know if that's right or not. Yep, 256 plus 81 plus 337. And then you would take a square root of that. And you would have, is that correct? Oh yeah. Okay, got it. Okay. Anyway, and then you would have V is equal to 18 point. Probably wanted to do something like 9.0. So it would just end up being 18 meters per second if we're doing the if we're doing, say, 9.0 there. If we're doing the proper sig figs. So 9.0 squared. Okay. Now if equals V squared there. Now, the other thing you might be asked is, what is the direction? And a lot of times what you want is you end up wanting this angle right here. So the other way we could draw that angle is we'd have 9.0 there and then 16 there. And so what we could say is we could say, okay, tangent of theta is equal to opposite over adjacent. So that means 16 over 9. Okay. And there's not really a decent sig fig rule for this. So the if you wanted to know the operation to do this to get rid of the tangent, you do the arc tangent. So what you'd have is you take an arctan of both sides and you'd get theta is equal to arctan of 16 over 9. So if you're looking for how to do this, so it would be arctan, I'm just going to put it on the computer, of 16 over 9. And a lot of times it'll give it to you in degrees. Dang it. And when you get that, you end up with theta equals 60.6 degrees. When it comes to the arctan operation, I'd typically just round to one decimal place. It seems to be pretty reasonable. So that is how you would do that one. Okay. One thing to keep in mind is that a lot of times your scientific calculators will be in radians. So when you do an arctan, you need to do a reality check to see if that degree, that level makes sense. So for instance, when I did this, when I initially did this, if you just do arctan of 16 over 9, you get, what do you get? I'll just do this. You get 1 point, your calculator might spit out like 1.05 or 1.06 to you. It's important to know that that's not 1.06 degrees. That's 1.06 radians, okay? And you can kind of tell that there's no way you're going to have a triangle with 9 on one side and 16 on the other side and have that angle only be 1.6 degrees. Okay, 1.6 degrees is tiny. That's almost horizontal. And you know certainly this thing is not going almost horizontal. It's, you know, it's going mostly up, in fact. So you'd have to, sometimes you need to do a reality check to know, okay, am I dealing in radians or degrees? And a lot of times, like I say, these calculators, they work in radians because radians is a lot of times a more useful measure. But that's neither. But again, just be clear on what you're doing and make sure that you've done that check. Okay, so that's important to know. One last thing is that I want to talk about is vector notation. Basically, a vector A, it's written like this, A, and then you'll see an arrow over the top of it. That indicates that it is a vector, which means it can either be expressed as a magnitude and an angle, or it can be broken into components. Okay. If you do something like this and you put an absolute value, this is just the magnitude of A. So that's stripping it of the angle, and you're just looking at the the magnitude. So that would be the hypotenuse of that triangle. Then you can also do this, A sub x and A sub y, and this would be the x component of A. And A sub y would, of course, be the y component of A. So that's just a few notation things to know regarding vectors. And I'll be using that as we go through. Okay, so hopefully that kind of stuff makes sense. There was nothing on this in the first assignment, even though I'm posting this in the first week. There will be some problems in the second assignment. So so I definitely encourage you to take a look at that. Make sure all of this stuff makes sense. But I'm going to go ahead and end things there. So thank you for joining me. I will see you next time.